Good afternoon, everyone. Our lab is on projectile motion, and our lab members are Anna, Haley, Amy, and Ellie. So this lab is focused on projectile motion and how its different parts, vertical and horizontal, are independent. This is an important concept in experimental physics and also has many real-world applications.
So the objectives for this lab are predicting where a projectile will land using physics equations to calculate the distance it will travel, experimentally verify the previous prediction, and use graphical analysis of projectile motion to demonstrate that horizontal and vertical motion are independent. So during this lab, when the ball is launched horizontally, its horizontal motion has a constant velocity and its vertical motion has a constant acceleration due to gravity, which creates a parabolic trajectory. You can see in that top corner. And in this lab, we are predicting the distance that the ball will travel after experiencing projectile motion. And to calculate the distance, we can use the equation d equals v times t. And to calculate the time of free fall, we can use a kinematic equation h equals viy times t plus 1/2 at squared, where h is the height of free fall, or the height of the table, and viy is the initial velocity in the y direction in meters per second. A is the acceleration due to gravity, which is 9.7966 meters per second squared in this ring. The t is the time in seconds. And since the initial velocity in the y direction is 0, when solving for t, we get that t equals the square root of 2h over a. You can see the work done in that bottom corner. And so since both the height and the acceleration are constant throughout the lab, we can assume that the time of free fall will always remain the same. To calculate the velocity, we know that potential energy equals kinetic energy, or mgh equals 1/2 mv squared plus 1/2 I omega squared, since the rolling ball has both translational or straight line and rotational energy. In this equation, m is the mass in kilograms, g is the acceleration due to gravity, which is 9.7966 meters per second squared, h is the height of the ramp this time in meters, v is the velocity in the x direction in meters per second, I is the moment of inertia in kilograms times meters per second squared, and omega is the angular velocity in radians per second. Since we know that the moment of inertia is 2/3 mr squared, since the tennis ball is a hollow sphere, and omega is v over r, when solving for the velocity, we can calculate that v equals the square root of 6/5gh, and you can see the work done in that bottom corner. So in the first activity, when we were changing the angle of the ramp, we can use trigonometry to find that the height is L sine theta, where the height is the height of the ramp, L is the length of the ramp, and theta is the angle in degrees. So then plugging this into the previous equation, we get v equals the square root of 6/5 gl sine theta, and using this and the time we solve for, we can calculate the distance. In the second activity, since we know the height, we don't have to solve for it, and we can just use the equation v equals the square root of 6/5gh. And using this and the time, we can calculate the distance. And finally, in the third activity, looking at the equation for distance, where the velocity is 6/5gh and the time is 2h over a, since mass is not included in either equation, we can assume that the mass of the ball will not affect the horizontal distance traveled when dropped from the same height and angle.
So the materials that we used were a ramp, a meter stick, a tennis, ping pong, and golf balls, a stopwatch, a scale for weighing, and then random boxes and blocks to change the height of the ramp. And I'm going to show you our methods.
But you should hold this and look just over here what's showing up so that you know. Oh no, don't do it yet because I need my phone. So when you are ready, go.
Okay, so we set up the ramp with 5 varying heights, which we used different blocks to manipulate the height for activity 1. And we, at the same height, released the tennis ball and then measured its projectile motion based on the distance it traveled from that height. And then this was compared to the calculated expected lengths for that height. Then for activity 2, we use the ramp with the same height and the same angle. And again, used the tennis ball, and we dropped it this time from different lengths along the ramp and measured its projectile motion and compared it to the calculated expected values. And then for activity 3, we used 3 balls and dropped them all from the same height. And again, we measured it, but pretty much used this experiment to prove that mass does not have an effect on velocity.
Okay, so for activity 1, we observed that as the angle of the ramp increases to a steeper angle, the range increases, evidenced by a positive slope in a graph of the horizontal range of the projectile and the ramp angle. And this graph has an R-square value of 0.9814, which is very close to 1, which indicates that our trials were consistent. We also compared the predicted range distance to the actual distance for each trial, which gave very low percent errors, which were 2.5% for trial 1, 5.4% for trial 2, 5.2% for trial 3, 4.6% for trial 4, and 5.2% for trial 5. In activity 2, we observed that as the starting distance increases higher up on the ramp, the range increases, evidenced by a positive slope, as you can see here in a graph of range versus starting distance from the end of the ramp. The graph also has an R-square value of 0.9754, which is close to 1, indicating consistency between trials. We also compared the predicted range distance to the actual distance for each individual trial, which also had very low percent error values, which were 4.2% for activities 1 or trials 1 and 2, 6.8% for trial 3, 5.5% for trial 4, and 4.2% again for trial 5. For activity 3, we observed that as the mass of the ball increases when we use different balls, the range does not change, evidenced by a horizontal slope with a value of m equals 0.0006 and a graph of range versus mass. This is a very low absolute error value of 0.0006, and we used absolute error instead of percent error because the expected value is 0 of a horizontal slope. So in conclusion, in activity 1, increasing the ramp angle increases the velocity of the ball, thereby increasing the horizontal range. The positive slope in a graph of range versus ramp angle accurately represents the direct dependence of projectile range on ramp angle. In activity 2, increasing the ball's distance from the end of the ramp where it drops increases the velocity, thereby increasing the horizontal range. The positive slope in a graph of range versus starting distance accurately represents the direct dependence of projectile range on the starting distance. And in activity 3, increasing the mass of the ball should have no effect on the velocity of the ball, therefore not influencing the range. The horizontal or 0 slope in a graph of range versus mass accurately represents the independence of the mass of the projectile and its range. The accuracy of the results of all of our activities are verified by our low percent or absolute error values and R-square values that were close to 1. And some sources of error include consistency in human observation, such as using the stopwatch to time when the ball fell off the edge to where it landed on the ground, and also the observation of the exact distance that the ball landed, since we can only, measure it to about the accuracy of 1 centimeter.
So during our research for this presentation, we found that the person that originally discovered that projectile motion has 2 components was Galileo in the 16th century, and he used ramps and balls similar to our experiment. And the real world applications of this are that, like sports, and also you can use projectile motion to do the field of ballistics or forensics or even aerial delivery of items. So this is our presentation. Thank you for listening.